the number of electrons that will flow through the wire depends upon both of the half cell. It is a relative thing, so we cannot measure the electrode potential of a single electrode, nor when we also cannot measure the exact electrode potential of an electrode when it is joined to any electrode. That's the main problem. So we should need a reference. Now the reference electrode. This is a reference electrode. Here what should be done? That reference electrode is nothing but SSE. Okay, reference electrode is the standard hydrogen electrode. What is the standard hydrogen electrode? We must see what is the construction. Okay. So it is a half cell taken for reference. Okay. What are the constructions? Very simple. There should be a vessel. It should contain first of all, electrolyte. The electrolyte is 1 HCl. Inside which one glass tubing is here, and your one platinum wire connects to a platinum plate. This platinum wire connects to a platinum plate, and through which hydrogen gas at 1 atmospheric pressure is bubbled through it. So the construction is a platinum wire connects to a platinum plate. The electrolyte is 1 HCl, and hydrogen gas at 1 atmospheric pressure is bubbled through it. Now, so this is the standard hydrogen electrode. As I said, this is the platinum wire, and this is the platinum plate, over which finely divided platinums are pasted, over which hydrogen gas can be absorbed. As you know, platinum has great affinity for hydrogen. Okay. So once you made ready the standard, the reference electrode, now you can join any of the half cell with it to have a standard value of electrode potential. Since it is a reference, now we can compare the electron producing or electron receiving capacity of an electrode. How? So let us first consider the electrode potential of zinc. Okay, so now we have to connect this zinc half cell to the standard hydrogen electrode to measure the electrode potential of zinc. So what should we do? Here, as we said, this is the zinc sulfate solution, and we should take 1 molar concentration. You see why we are taking 1 molar concentration. So as we said, the electrode potential, there is another term, standard hydrogen electrode. Okay, standard electrode potential. Standard electrode potential. Electrode potential to standard electrode potential. Okay. What is the standard electrode potential? When we measure the electrode potential at standard state, what are that standard state? When we measure the electrode potential, taking the concentration of the electrolyte, should be 1 molar. Temperature should be 25 degrees centigrade, the room temperature, and the pressure, if any, should be maintained 1 atm. If you measure the electrode potential at these conditions, then the electrode potential will be called as standard electrode potential, and that's why in standard hydrogen electrode we have taken 1 molar hydrogen chloride as electrolyte. Well, we have also taken the 1 molar concentration of the zinc sulfate solution. Okay. So in the zinc sulfate solution, we will have to dip a zinc electrode. Okay, we will have to dip a zinc electrode, and this zinc electrode must be connected to the hydrogen electrode. And as usual, there should be one, what is this? Yes, salt breeze. Okay. Now, you see what happens. When you connected this zinc half cell with the standard hydrogen electrode, after some time, when we got a steady voltage, of 0.76 volt. In particular these conditions, we can make an experiment, and also we can get that steady constant voltage of 0.76 volt. Then how to measure the electrode potential? It is now very easy to understand. Okay, you see, let me tell you that this voltage is due to the extent of electrons that is flowing through the wire, and again the extent to which electrons are flowing through the wire depends on how the electrons are produced in the oxidation half cell and how much electrons is produced in the reduction half cell. But problem once again is which of them is the oxidation half cell and which of them is the reduction half cell. Did you get me now? So after some time, when you got a steady voltage, when you measure the concentration of hydrogen ion inside this standard hydrogen electrode, the H plus ion concentration was observed to be less than 1 molar. But we have taken 1 molar hydrochloric acid. So that means it should give us the concentration of hydrogen ion 1 molar. But we are getting less than 1 molar. That means hydrogen ion has been used up to give hydrogen gas. Each hydrogen ion must receive 1 electron to give H. Such like this, 2 hydrogen ion receiving 2 electrons give hydrogen gas and is released. So since the hydrogen ion concentration is decreasing in this chamber, that means here electrons is received by the hydrogen ion and becoming H2. So since electrons received, this is the reduction half cell. The standard hydrogen electrode is now in this case only reduction half cell. Okay, reduction half cell. So definitely, if electrons is received, S plus ions here there are S plus ions. Those S plus ions are receiving the electrons coming from here, and since reduction is taking place here, then oxidation must taking place in this chamber, zinc half cell. How? So zinc is being oxidized to give Zn2 plus and 2p minus. The electrons produced in the zinc half cell is flowing through the wire and received by the H plus ions, and H plus ion being H2 is released. So we knew now which of them is the oxidation half cell, which of them is the reduction half cell. Okay. Now it is very clear that the voltage we are obtaining, that steady voltage of 0.76 volt, is due to the extent to which the oxidation half cell is oxidized and the reduction half cell is reduced. So we can say this voltage is a result of the oxidation potential of this electrode and the reduction potential of this electrode. Oxidation potential means the readiness, the tendency of an electrode to be oxidized. Reduction potential means the extent to which one electrode wants to be reduced. So whatever the combined effect of the oxidation potential and reduction potential is nothing but this voltage. So now we have made a cell. It is nothing but a cell, no? So now the voltage will be called as cell potential. This cell potential is a combined effect of oxidation potential and reduction potential. Okay, so we will write accordingly a formula. Okay, so we can write the electrode potential we got, the cell potential we got, the cell potential, and we call it EMF, electromotive force, cell potential. If we measure them at standard state, then that will be called as standard cell potential. We write it E0 cell. It's nothing but the combined effect of both of the halves I have already mentioned. So it's equal to oxidation electrode potential of anode. You see, let me tell you that from now, whenever I will write anode, you will have to take it oxidation electrode. The electrode where oxidation takes place is the anode. You see, you remember it. Anode means oxidation half cell. Cathode is inside reduction half cell. Remember it. Okay. Remember it. Okay. Write it down. So now the standard cell potential is equal to oxidation electrode potential of the anode plus reduction electrode potential of the cathode. Okay. So the first formula is nothing but the E0 cell means standard cell potential is equal to the sum total of the oxidation electrode potential of the anode and reduction electrode potential of the cathode. And accordingly we can develop this equation continuously. In this instance, in this example, zinc was being oxidized, hence zinc acts as anode where oxidation takes place. And SHE in standard hydrogen electrode, you know what happens? The reduction takes place and that acts as the cathode. Did you get it? So accordingly, we will give a notation to both of these. Okay. So you now see, you are saying oxidation electrode potential of anode. If we will change this reduction into oxidation, then I can change this sign positive to negative. So I can write E0 cell is equal to oxidation electrode potential of anode. When I change this positive to negative, this reduction once again is changed to oxidation. Oxidation electrode, all other terms will be remaining there. Oxidation electrode potential of cathode. This is one another formula. Similarly, if you want to, that means make it as usual to be retained in the equation, and if you want to change this oxidation into reduction, that should get a negative sign. So accordingly, you can also get E0 cell is equal to take it to the first reduction electrode potential of cathode minus the reduction electrode potential of anode. this formula particularly is of greater importance because nowadays the electrode potential of all the electrodes are generally expressed in terms of their standard reduction electrode potential. That's why this formula should be that means remembered with importance. Okay. So how to give a notation? See now, since we have taken the standard cell potential E0 cell to be the oxidation electrode potential of the anode. Here the anode is nothing but the zinc half cell where oxidation takes place, and the redox with it we should add the reduction electrode potential of the cathode. In this instant, this is standard hydrogen electrode. Are you getting me now? So we can now write standard cell potential E0 cell, which we have already measured from the voltmeter to be 0.76 volt, is equal to the oxidation electrode potential zinc half cell or anode in this case. How to represent it? It is represented like this. E0 in the oxidation half cell, it is becoming E0 Zn becomes Zn2 plus. This is the oxidation half cell. Charge is increasing, and by this notation, since 0 to 2 plus, it is mentioning you the oxidation electrode potential plus this is E0 plus. In the standard hydrogen electrode, what happens? Hydrogen ions being reduced, so 2H plus receiving electron to give H2. This is the perfect notation now. This is, we can say, the oxidation electrode potential. Charge is increasing of the anode and the charge is decreasing plus to 0. That means reduction. The reduction electrode potential of the cathode. So conventionally, let me tell you one thing, that when we constructed the standard hydrogen electrode, we have conventionally taken the electrode potential of that standard hydrogen electrode to be 0, so that whatever you have to connect all those electrodes with that, so there is no problem. So we can write, so its electrode potential, in the note you should write standard electrode potential of SHE is conventionally taken as 0. So implies 0.76 volt is equal to E0 Zn2 plus 0. That means this is equal to this. So E0 Zn2 plus means this is the standard oxidation electrode potential of zinc is equal to 0.76 volt. Thus, we measure the electrode potential of the zinc electrode. Did you get me now? So we can write, you see here, E0 Zn2 plus Zn2 plus Zn means this is standard reduction. Since charge is decreasing 2 plus to 0, reduction electrode potential of zinc, just the negative sign of it. Since this is being converted oxidation to reduction, this should be 0.76 volt. 0.76 volt. I now think that you got properly what is electrode potential, what is standard electrode potential at the standard state when we measure, what is standard hydrogen electrode, that is our reference electrode, with which you have to couple another half cell for which you want to calculate the electrode potential.